Alright, I'm just going to show you another method here that can be used. Let's say you wanted to decompose this into partial fractions. So we know that you can write this, since there's three linear factors, you can write this as a over the first linear factor plus b over the second linear factor plus c over the third linear factor. Okay? Well, what you can do is you could do, there's three things we can do here. First of all, let's say we're going to multiply everything by only the first linear factor x minus 1. So if we multiply the left by x minus 1, we would get x squared plus 1 over x minus 2 times x minus 3. And then this term, the x minus 1 would cancel, so I'd get a. But then I'd have to multiply each of these by x minus 1. So now let's set x equal to 1, and then we'll get that a is 1. Let me show you how that works. Let x equal 1 on the left, and you get 1 squared plus 1, which is 2, right? And then on the bottom you get 1 minus 2 times 1 minus 3, so that'd be negative 1 times negative 2, right? So that would give you 2 on the bottom. So you get 2 on the top, you get 2 on the bottom, and 2 over 2 is 1. Now, how do I know a is 1? Well, because since I set x equal to 1 on the left, if I set x equal to 1 in this term, then that's going to go to 0, and if I set x equal to 1 in this term, that's going to go to 0. So that's called the kind of the cover-up method. So we can kind of cover up these by letting x equal 1. We can kind of cover these two up, and we just get a equals 1. So we know a equals 1. Now let's cover up the x minus 2 factor. So if we multiply everything by x minus 2, then here's what we would get. Here's what we get. If we cover up the x minus 2, then we would get just b on the right, because basically we'd be multiplying both of these by x minus 2, and we're going to find b by setting x equal to 2. So if we set x equal to 2 and both of these have a factor of x minus 2 in them, then they would disappear, and I would just get b, and then I could plug 2 on the other side to see what the b equals. So if you plug 2 on the other side, I get 5 in the denominator. Now remember, we covered up the x minus 2, so I get 5 in the numerator, and if I plug the 2 in here, I get 1 here, and then 2 minus 3 is negative 1, so that's going to give me 1 times negative 1, which is negative 1, so I have 5 over negative 1, which is negative 5. So b would be negative 5. And then last, let's cover up the x minus 3. So to cover up the x minus 3, basically what that would do is that would cover this up, and it would cover this up, and then I'd be multiplying both of these by x minus 3. Okay, and so I mean, that's how I get those to disappear, by the way. So then if I let x equal 3, these two terms would both disappear, and they would disappear, and all I would get would be c on the right, and then I could plug 3 in over here to see what I get on the left. And so 3 squared plus 1 is 10, and then on the bottom 3 minus 1 is 2, 3 minus 2 is 1, so I get 10 over 2, which is 5. So I get c equals 10 over 2 equals 5. So it's kind of a clever little technique that you can use by manipulating those factors. Now, since I know that, since I know a is 1, I can write the first factor, the first term, as 1 over x minus 1, and since I know b is negative 5, I can write this as negative 5 over x minus 2, or I could just say minus 5 over x minus 2. And since c is 5, I can write the third factor as 5 over x minus 3. And so by knowing a, b, and c, I know how I can rewrite this. And there's a problem there that you can read, basically the same thing. Let's see here, what did I do there? If you cover up x, and let x equal 0, then these terms would disappear, and if you plug 0 in, you'd get 4 over let's say 4 over negative 10, which is negative 2/5. And then if you cover up the x minus 2 and let x equal 2, so you'd cover up the x minus 2's here and then let x equal 2, and it would get rid of these two. And then if x is 2, you'll have 6 over 2 times 7. So 6 over 14 reduces to 3/7. And then last, if you cover up the x plus 5, then this would disappear, and this would disappear. And since these are multiplied by x plus 5, you would let x equal negative 5, and that way these terms would disappear. And then just plug negative 5 in here, and you'd get negative 1 over negative 5 times negative 7. So that's negative 1 over 35, which is 1 over 35. And then you could write that, well, basically you could write this as negative 2/5 over x, which is negative 2 over 5x. And I went ahead and just factored the negative 2/5 out. And then this you could write as 3/7 over x minus 2, or just factor the 3/7 out, and then that'd be 3/7 times 1 over x minus 2, and then this 1 over 35. So if you factor the 1 over 35 out of there, you would get 1 over 35 times the integral of 1 over x plus 5 dx. Now again, I didn't integrate these, but the point is now that you've been able to rewrite this fraction as the sum of these three fractions, now you have these simplified to forms that now can be integrated. Okay, I wanted to show you one more thing real quick. Earlier, you saw me earlier. Let me go back and show it to you. Okay, so in an earlier example, I actually had this expression here written out, and what I did is I think I actually wrote it down here like this. So I think this is where I want to be. Okay, so I had it in this form: 5x cubed minus 3x squared plus 2x minus 1 equals a plus c times x cubed plus b plus d times x squared plus ax plus b. Okay, now I'm going to copy that down here. Okay, so here's the same expression. Okay, now here's what we're going to do. I'm going to do something interesting here. Let me show you. This is a little trick that I saw done in the book. Let's say you take the derivative of each one of these terms. So the derivative of 5x cubed is 15x squared. The derivative of minus 3x squared is minus 6x. The derivative of 2x is 2. The derivative of negative 1 is 0. And then if you take the derivative of this, remember a plus c is a constant, so you'd have 3 times a plus c x squared. If you took the derivative of this, you'd have 2 times b plus d times x. If you took the derivative of ax, you would just get a, the coefficient. And if you take the derivative of b, you get 0. So now, if you distribute the 3 through here, you get 3a plus 3c, and then each of these times x squared, so you get 3a squared plus 3c squared, 3ax squared plus 3cx squared. And then here, if you distribute the 2, you get 2 times b times x, and you get 2 times d times x, and then bring the a down. So now, you can see here that if you took the x squared out of these two, you get 3a plus 3c x squared. So you know 3a plus 3c must equal the 15. And then here, the 2b plus 2d, if you factor the x out, you get 2b plus 2d times x. And so you know the 2b plus 2d must equal the coefficient of x, which is negative 6. And then here we know that a must equal the constant, 2. So basically, you can see that a is 2, and then you could plug this 2 back in here, and you would get 6 plus 3c equal 15, and then you could, solve that for c and get c equal 3. And then what would we do here? 2b plus 2d equal -6. I guess we would have to go back up there from earlier. Earlier we knew that b was -1, so I guess that doesn't help me get all of the values, but I'd still have to go back and get b equal -1. But that's just a little trick I saw them do in an example. They were able to, instead of equating the coefficients of this expression, they were equating the coefficients of the derivative of that expression. So anyway, if you're interested in this method, you can probably search Google or YouTube and find some more examples. Okay, so that pretty much ends the section on partial fraction decomposition. And the next section, we're going to talk about evaluating integrals involving trigonometric integrals.